There is so much fascinating chemistry going on in this cup of coffee right here. I could talk about the bioactive compounds in coffee, like caffeine, which is a psychoactive drug, a stimulant. I could talk about the chemical reactions involved in the process of roasting the coffee, like the Maillard reaction, which is like the reaction in molecular gastronomy. But the thing I personally find the most interesting about this cup of coffee is that it contains several types of colloid. Here, is this ASMR? Hello and welcome to my channel, Finn Does Chemistry. I'm Finn and I really love coffee, so I've been super looking forward to making this video, especially because I can talk about colloidal materials. You may have never heard of colloids before, but you've definitely come across them in your everyday life. So in this video, I'll cover what a colloid is, the 8 different types of colloid, how they are structured, and which ones you can find in your bean brew. By the way, do you guys like my little colour changing Animal Crossing mug? Thermochromic, that's what we call it in chemistry. Hey, if you want to see a video about thermochromic materials, comment down below. So first off, what actually is a colloid? So we all know the 3 main phases of matter: solid, liquid, and gas. You know, you could argue that there are others like liquid crystals or plasma, but these are the big 3 that we're interested in. And a colloid or colloidal material is basically a really fine mixture of 2 of these phases. For example, if you have solid particles, if you have solid particles in a liquid continuum, then that is a colloid. Sometimes you can't just throw some gravel in a glass of water and call it a colloid. Colloids are specifically made of particles 1 nanometer to 1 micrometer in diameter, and these particles are then dispersed evenly throughout the other phase. We call the 2 phases the dispersed phase and the continuous phase. And in a colloidal material, the dispersed phase does not settle out because of gravity. The particles do not accumulate and clump together until they become particles more than a micrometer in diameter, and you can't filter or separate out the 2 phases. I think it's easiest to understand with some everyday examples of colloids. Now, there are 8 types of colloid which are categorized based on what the continuous and dispersed phases are. Let's start with the colloids where the continuous phase is a solid. A solid-in-solid colloid is called a solid dispersion or a solid sol. An example would be a metal alloy where you've got tiny nanoparticles of one type of metal dispersed throughout another metal. Steel is a solid dispersion of... gosh, I'm gonna have to look up what's in what. What is steel made of? Worldsteel.org says steel is an alloy of iron and carbon containing less than 2% carbon and 1% manganese and small amounts of other things. So there, the continuous phase would be the iron, and you're going to get small particles of carbon and manganese throughout, and that is the dispersed phase. A liquid in solid colloid is called a solid emulsion or gel, and an example of that is gelatin. And then a gas in solid colloid would be a solid foam, like styrofoam. Moving on to colloids with liquid as their continuous phase. A solid in liquid colloid would be a sol, and I think possibly the most important sol on Earth is blood, because, you know, it keeps us alive and stuff. A liquid in liquid colloid is called an emulsion, and a great example of that would be milk. And I should say a colloid will only form between 2 liquids if they are not miscible, which means they don't actually fully dissolve in the other liquid. And we'll talk a little bit later about why that's important. And finally, a gas in liquid colloid is going to be a foam, like shaving cream. Finally, moving on to colloids where gas is the continuous phase. If you have particles of solid suspended in gas, that is a solid aerosol. An example of that would be smoke, which is small particles of black carbon of soot suspended in the air. And for a liquid, it's just a liquid aerosol. An example of that would be clouds. And finally, you'll see we have left 1 box blank at the end here. You might have noticed earlier I said that there were 8 different types of colloid, and that's because a gas-in-gas colloid doesn't really exist. If you mix two gases together, the particles will tend to travel around as individual molecules. They do not cluster together with other molecules of gas their type, which means that the individual particles of gas are not a nanometer or more in diameter. So a mixture of two gases is just that, a mixture. So now that we know the 8 types of colloid, which ones are present in a cup of coffee? To answer that, let's think about what components are actually in a cup of coffee. I am personally partial to a flat white, so that's the coffee that I'm going to go with for this video. In a flat white, you have got the actual espresso shots, the actual coffee bit of the coffee. You've got your steamed milk, and then maybe you like to add some sugar or syrups into there. So let's take these components one by one and decide whether or not they're colloids. Let's start with the bulk of our cup of coffee, which is the milk. Milk is an emulsion of about 2% fat in water. If we want to be able to tell whether the particles are colloidal in size, we can use something called the Tyndall effect. This is the scattering of light by the dispersed phase particles in a colloid. You can think of light as a wave of electromagnetic radiation, and the wavelength of that wave for visible light is around 400 to 700 nanometers. And remember, the particle size of the dispersed phase in a colloid is anywhere between 1 nanometer to 1 micrometer, which is 1 to 1,000 nanometers. And you'll notice that the range of visible light wavelengths falls within the range of particle sizes. When a ray of light with a wavelength roughly equal to the size of the particle in the colloid, those particles can actually interfere with that wave of light and scatter it in a process called me-scattering. And what this does is it makes the beam of light visible when you're viewing it from the side. An example would be, you know, when you get a ray of light coming through the window and you can see that ray of light reflected on the dust particles in the air, that is the Tyndall effect in action in a solid aerosol. I think we should turn this into an experiment. Maybe after I finish this cup of coffee, actually.
A few moments later.
So this is just a glass of water. We're gonna try shining a beam of light through it, and let's just see what happens. I'm gonna turn the lights out. So when I shine the beam of light through the water, there's a couple of little air bubbles in there from where I just had the tap on, but for the most part, the beam of light is not visible. And then this is with a glass of milk. I've watered it down just a little bit so that the beam of light is more visible. But there you can see that the ray of light is scattered. So we know that milk is a colloid of fat in water. But the eagle-eyed among you might have noticed something a little bit strange going on, because fats and water do not mix. A great example is cooking oil, which is mostly made of triglycerides and water. These two liquid phases will just completely partition from each other. So how do the fat and water in milk form such a homogeneous, fine mixture? The key is in casein, which is a protein found in milk that acts as an emulsifier or surfactant and stabilizes the phase interface between the oil and the water. Water is a polar molecule. There are charge gradients within the molecule with a slight negative charge on the oxygen atom and slight positive charges on the hydrogens. This is because oxygen is more electronegative than hydrogen, which means that it pulls the electron density in the oxygen-hydrogen bonds towards itself. Electrons are negatively charged, so when oxygen does this, it ends up with a slight negative charge, which we write with this little delta minus symbol. And likewise, because the hydrogens have lost negative charge, they end up slightly positively charged. And opposite charges attract each other, so neighbouring water molecules can form favourable stabilising interactions between them called hydrogen bonds. Now, hydrogen bonds are not true chemical bonds in the same way that the bond between the oxygen and the hydrogen within the water molecule is a covalent bond. Hydrogen bonds are just what we call this favourable interaction between the two charges. In the case of the oil, fatty acid chains, which make up the majority of the triglyceride molecule, are long hydrocarbon chains. which means it's all carbons bonded to other carbons and carbons bonded to hydrogens. Now, carbon and hydrogen have very similar electronegativities, so there is not much polarity in those bonds at all. We think of hydrocarbon chains as almost entirely non-polar. However, favourable interactions between these long carbon chains do exist, and these are called London dispersion forces. This is a bit more tricky to explain. It involves neighbouring non-polar molecules being able to induce some polarity in the other by polarising the electron field, and that results in an attractive force. But the important thing is that forms an attractive force in between hydrocarbon molecules. These forces are much weaker than hydrogen bonds, but they are present nonetheless. So when you have a mixture of a polar liquid like water and a non-polar liquid like our oil, each individual molecule will tend to stick with other molecules of the same type. Water molecules are most stable when surrounded by other molecules of water because they can form favourable hydrogen bonding interactions, and fatty acids are most stable when surrounded by other fatty acid molecules. This is why your oil and water will separate into two different liquid phases. To get these two phases to mix, we need something called a surfactant. Surfactants are special molecules which are amphiphilic, which means that different parts of the molecule are soluble in polar or non-polar solvents. A great example of where you can find surfactants is in washing up liquid. Your washing up liquid probably contains either SLS or SDS, sodium lauryl sulfate or sodium dodecyl sulfate. And you'll notice that these molecules have a charged group on one end, which makes this part of the molecule very, very soluble in water, and then a non-polar hydrocarbon chain. And this hydrocarbon chain is, of course, more soluble in the oil phase. If these surfactants are present in a high enough concentration, we can form what's called micelles. Micelle formation is when the surfactant molecules stabilise the phase interface in between the oil and the water, which means that you can have a small particle of oil stabilised by the surfactant within the water, and it's perfectly happy to sit there as a little particle. So this is just the oil in the water, and as you can see, it forms the two different phases. And there's a very clear interface where the two phases have separated. So now I'm gonna go and get our surfactant. It's literally just it's fairy liquid. I'm getting some fairy liquid. It's actually not fairy liquid, it's Tesco own brand washing up liquid. Hashtag not sponsored. Does it say which surfactant it is? No, it just says anionic surfactant. So that's probably SLS or SDS. They're the most commonly used. But I'm hoping what will happen is this will break up the phase interface because it will stabilize. We might even get a colloid out of it. We'll see. Yummy. Whoa. Oh my gosh, it's like a lava lamp. Wait, come close, come close. Yo! So now I'm just mixing it. I'm just giving the washing up liquid an opportunity to interact with both of the phases. So some of the washing up liquid is just sunk to the bottom here because it's really dense, but you can see that phase interface has really broken up because it's been stabilised by the surfactants in the washing up liquid. Should we see if there's colloids in here? I think we should see if there's colloids in here. Oh, would you look at that? We have made a colloid. You can see the beam of light being scattered. Oh, this looks really f***ing sick. It's also kind of disgusting, but it's kind of cool. This is exactly what's happening in milk, except in milk, the protein casein is the surfactant instead of a SDS or SLS surfactant. And casein has a much more complicated structure, but it works broadly in the same way. There are polar and non-polar parts of the protein which are soluble in water and oil respectively, and what we end up with is a colloidal emulsion of oil in water. Now, if you add sugar or syrups into your coffee, those are not going to form a colloidal material. And that's because sugars are highly polar, which means they are soluble in water without any stabilization required. You'll notice that a sugar like this has a lot of OH groups, which means that it can actually form hydrogen bonds with the surrounding water. And because it can form favorable interactions like this, sugar molecules don't go around as clusters, as colloidal particles. They will completely dissolve and travel around as individual molecules. Anyways, let's move on to another part of the cup of coffee. You've got your milk, which is an oil and water emulsion. But if you have your coffee with the milk steamed, like I do, that's another colloid right there. If the steaming process is done right, you will get tiny little bubbles of air in the milk. And this is, of course, a foam. It's a foam of an emulsion. It's like a colloid in a colloid. Something I will say though is if your coffee looks like this, that's not a colloid, those are just air bubbles. I used to be a barista, so I'm like a little bit fussy about my steamed milk. We want that nice colloidal steamed milk. If it's done right, you won't get any visible bubbles to the naked eye. Instead, you get this almost sheen on the milk while it's being steamed, and that's when you know. That's when you know it's the good stuff. It almost looks a bit shiny. It looks a bit like paint. And then when you drink it, it like really fulfills that urge to drink paint. Is that weird? I don't think that's weird. I thought it was shut up, let's move on. Now let's think about the actual coffee part of the coffee, the espresso shot. This is made by flowing hot water over coffee grounds, and in the process the water extracts anything soluble. So most of the good stuff in the coffee acts similar to the sugars we discussed earlier, in that they don't form colloids, they are just soluble in the water as individual molecules. However, there are also some oils present in the coffee. There are a few types of diterpene, I think, and I believe the main stabilizing surfactants in a shot of espresso are melanoidins, I think. Fact check me on that. I could look it up now, but I can't be arsed. So that right there is another emulsion. Now there are also insoluble solids in an espresso shot, and I'm sure there are situations where this forms a sol colloid, but typically these solid particles settle out. If you've ever had a cup of coffee and had some grounds left at the bottom, that's what's happened. These solid particles have settled out of solution, and because they settle, they separate out from the bulk of the liquid. They are not true colloids. Now, the final colloid I want to talk about is a little bit less obvious. When you see the steam rising off your cup of coffee, do you ever think about why that steam is visible? If it was just a gas, it would be invisible just like the oxygen and nitrogen in the atmosphere. No, the reason we can see it is because the particles are the right size to scatter light. It's like the Tyndall effect again. This steam is a liquid aerosol on a short time scale, at least, before it then evaporates off and dissipates. As the steam dissipates, the water that forms the particles just evaporates off, and the particles get smaller and smaller until they entirely evaporate and the water is just a gas. The lifetime, I guess, that the aerosol stays an aerosol is dependent on things like the humidity in the air, the temperature, because if the air is more humid or the temperature is lower, that means the air is closer to approaching its saturation water vapor pressure. And hey, if that's something you're interested in, I have good news for you. I just did a video which explains saturation water vapor pressure, so if you're interested, go check that out. I think is it gonna pop up here? I hope it will. Yeah. Saturation water vapor pressure and how it results in cloud formation. Pretty cool. Thank you so much for watching, and see you in the next one. Bye.